All right, we want to talk about a paired T, and we're going to talk about something called robustness. I referred to it earlier. With match pairs design, you can use T procedures. So remember match pairs, you compare left hand to right hand, you compare twins, you compare before and after, things like that, okay? Looking for a difference in treatments. So we're still going to use panic, but what we're going to do is we're going to take so this is based on people who were all addicted to caffeine, and then they have them stop having caffeine from coffee and tea and chocolate, but they instead take a caffeine pill. And we measure their depression. They measured something else, their heart rate or something, compared to when they had caffeine pills versus placebo pills. And you can see there seems to be a pretty big difference in the depression here and here. Okay. And we want to check, is there a difference in depression? So what we want to do is I put my caffeine depression and placebo depression in L1 and L2. And what we want to look for is a difference between them. So I'm going to create L3, let it be the difference of, I'll do L2 minus L1 so I get mostly positive numbers, okay? So you go up here to L3 and you can say L2 minus L1. And now this is the difference. This is how much more depressed they were when they were taking a placebo, okay? And this person was less depressed. They weren't really depressed either time, but less depressed when they were taking a placebo. So the parameter that we're looking for is here, the true mean difference in depression between placebo and caffeine. Okay, the assumptions, these people were randomly assigned. Okay, so counts as a simple random sample because they were randomly assigned to treatments. Okay. Second, we see that it's independent because the randomness covers the independence of the two people or the two treatments, whether they were which one happened first or second, and then normal. Here we want to check and make sure that there aren't any outliers, shape, and a normal probability plot, okay? And I'll be doing more of that during class. So name the interval. This is called a paired T interval. But it's kind of like we end up doing one sample. So on my calculator, it's going to be a one sample T interval, but it's really from two samples, the caffeine and the placebo, okay? But we paired them so that we subtract them and get one column. We're doing L3 instead of L1 and L2. We combine them to get an L3, okay? If you're not combining them, it would be a two sample, which is not paired, okay? So my interval, let's see what we get. So if I come up here and I do stat tests, I can do a T interval. My T interval on my data, which is in L3, second 3. I can create a 95% confidence interval. And we find that 2.716, 2.72 to 12.01. 2.7 to 12.0. My interval so what would I say? Start out with, we are 95% confident that the true mean difference in depression for the placebo and caffeine is between 2.7 and 12.0. And really, what this means is it's not 0. 0 is not in the interval. We are have sufficient evidence to conclude that caffeine reduces depression. If there is a possibility that there is zero difference, we know that there is a difference. Okay? So there's sufficient evidence because zero is not in the interval. When zero is in the interval, then you say, oh, there might be no difference. But since zero is not in the interval, we have sufficient evidence to conclude that there is a difference. Okay? So the other idea I want to talk about is robustness. An inference procedure is called robust if the probability calculations involved remain fairly accurate when a condition is violated. Okay? So for confidence intervals, that means that the confidence interval is still fairly accurate when you make a subtle change to it. Okay? So T procedures, non-normality, especially if it's symmetric, it's robust. Okay? So non-normality, the central limit theorem will normalize it and we're in good shape. But outliers, not so much. Slight skewness, central limit theorem will take care of it. But strong skewness, not so much. And so when you're looking at, can I use a T procedure? You want to have it be relatively normal without any strong skewness. As soon as you have outliers or strong skewness, you're out of there, okay? But non-normality, even if it's bimodal, as long as it's symmetric, you're in good shape. Slight skewness, okay. Strong skewness, bad. Huge outliers, bad. Let me show you what I mean, okay? So remember this example, we talked about the Knox levels, okay? And we found this was our confidence interval, 1.1645 to 1.421. That was what we got. If we, or no, this is taking out the outlier. What we got last time when we did it was we got this interval, 1.185 to 1.473, right? Our sample size was 46 on the other one. Not much change, but my standard deviation changed when I got rid of the outlier. My mean went down. My standard deviation went down. This n went down by 1. And so what we see is we get a very different interval. This side changed by 0.2. This side changed by 0.5, okay? And so we're looking at a relatively large difference between the intervals, okay? 0.05, 0.02, when we're really looking at an interval like this, that's a pretty big shift. So is there a large difference between the two intervals? Yes. So are we 95% confident that it's in here or 95% confident that it's in here? Neither. Not 95% confident about either because the intervals have changed so drastically. And so is the T interval robust? No, T intervals are not robust against large outliers. Boom. Okay, if it's really far from the mean, really far outlier, T intervals are going to get slammed by those. Okay, so that is your idea of robustness. Good luck and farewell.